Part 4. Understanding corneal refraction. In the last video, Part 3, I have discussed how laser works and how to calculate ablation depth and K readings. In this Part 4, I will discuss corneal manifest refraction and corneal power maps. Actually, these two topics are related to each other, so they will be presented together. We will start by means of measuring corneal power. Corneal power can be measured by keratometry, anterior sagittal curvature map, anterior tangential curvature map, anterior refractive power map, true net power map, equivalent K reading power map, and true corneal refractive power map. Starting with keratometry. The keratometer measures the radius of curvature of the measured point and then applies the equation of P equals N2 minus N1 multiplied by 1000 and divided by R in millimeters, where P is the power of the point, measured point, N1 is the index of R, which is 1, N2 is the index of cornea, and it is considered by the keratometer to be as 1.3375, and of course this is the old wrong index, and R is the radius of curvature in millimeters. The keratometer measures the K readings at the ring of 3.2 millimeter of diameter, so at the ring, not inside the ring. So it does not measure a zone, it measures the ring. Now, from the keratometry developed the keratoscopy. The keratoscopy uses the same principle, but by using the Placido rings projected onto the cornea in order to study the curvature of the anterior corneal surface. After that came more advanced technologies. We call them scanning technologies, such as slit scanning, like Orbiscan, Scheimpflug imaging, like Pentacam, Cyrus, Galilei, and Tommy, and finally the anterior OCT. Now, from all these technologies, we can obtain a lot of maps, and I'm going to discuss these maps, and I will explain their clinical applications. Starting with the anterior sagittal curvature map. The anterior sagittal curvature map represents the power of the anterior corneal surface measured by the sagittal method. Now, what's the sagittal method? Suppose I want to study the power or the K reading at point A. I will draw the tangent to the surface at that point, and then I will take the normal to that tangent, which will intersect with the reference axis. The reference axis goes through the apex of the cornea. Now, the piece AB represents the radius of curvature at point A, and then the equation will be applied, and using the wrong index, which is 1.3375. So in the anterior sagittal curvature map, we use the sagittal method of measurement and the wrong index of refraction of the cornea. The anterior tangential curvature map, also the same wrong index, 1.3375 is used, but instead of using the reference axis, circles are used. The computer chooses the best fit circle to that point, and the radius of that circle is the radius of curvature at point A, and the equation is applied. The anterior refractive power map. The anterior refractive power map takes into consideration the difference in angle of incidence and therefore angle of refraction between the central part of the cornea and the peripheral part of the cornea. Therefore, it takes into consideration the spherical aberrations. It uses the Snell's law or the ray tracing, but using also the same wrong index of refraction, which is 1.3375. So the map represents not only the power, but also the high order aberrations, especially the spherical aberration. The true net power map. The true net power map is a combination between the anterior and posterior corneal power. It uses the Sagital method to measure each surface, but instead of using the wrong index of refraction, it uses the real index of refraction of the cornea, which is 1.376. The equivalent K-reading power map. Also, this power map takes into consideration both surfaces, and also it takes into consideration the spherical aberration because it uses Snell's law or ray tracing. In addition, it uses the real index of refraction of the cornea, which is 1.376. And finally, the total corneal refractive power map, which takes into consideration the anterior surface, posterior surface, and corneal thickness. So it takes into consideration corneal thickness, and it uses the true or the real or the correct index of refraction, which is 1.376, and uses the ray tracing or Snell's law in measurement. Clinical applications of these maps. The anterior sagittal curvature map is very important in order to study SIM case and to calculate the post-op K readings after refractive surgery. The IOL conventional formulas are based on this map. In addition, the anterior sagittal curvature map is a part of the 12 points algorithm in studying corneal tomography. Now, the very important thing to know about SIMKs is that the SIMKs are measured by the anterior sagittal curvature map and presented over a zone of 3.2 millimeters, but this zone is centered within the pupil. So the pupil center is used as the center of the zone of measurement rather than the apex of the cornea. So this is one of the reasons why we must not dilate the pupil before measuring or before capturing the patient. Otherwise, the K readings presented will be incorrect because the center of the pupil is shifted after dilatation. The same thing can be said when we capture the patient under incorrect circumstances of illumination. We must capture the cornea under mesopic circumstances of illumination in order to have as much real as possible of the center of the pupil. Otherwise, the SIMKs presented will be incorrect. The last thing is, from now on, we are going to adjust the settings of the device in order to display the astigmatism with the steep axis rather than the flat axis. So the steep axis will be used because the plus equations will be used in all our examples. The anterior tangential curvature map is important to describe cone shape because there are three shapes of the cone in keratoconus: the nipple, the oval, and the globus shape. These shapes are important in contact lens fitting and in studying or planning for some treatment modalities, and this is well discussed in my series of keratoconus on YouTube. The TrueNet power map is used to calculate the true K readings after keratorefractive procedures, and this is well discussed in part 6 of Concepts in Refractive Surgery video series on YouTube. The same can be said on the equivalent K reading power map. It can be used in calculation of the true K readings after keratorefractive surgery. In addition, it also can be used instead of SIMKs in conventional IOL calculations, and all of this is discussed in detail in part 6. Total corneal refractive power map. We use this power map to check manifest versus corneal refraction before refractive surgery, to determine the assumed manifest refraction in keratoconus and irregular corneas, and to calculate the toric aphakic IOLs. Starting with the first indication. Now we use this indication in order to check the manifest refraction that we obtained by subjective examination in order to test this manifest refraction against corneal refraction and to know whether there is a disparity, especially in astigmatism. Now we will discuss this topic by studying the translation between cornea power and the manifest refraction at a glass plane. And this can be done by two paths. Path number one is called inward translation. Path number two is called outward translation. Now starting with the first path, inward translation. In this path, we are going to translate the power of glasses or manifest refraction into the manifest refraction at corneal plane, and we call this corneal manifest refraction. So corneal manifest refraction is actually a projection of the manifest refraction at corneal plane. And we do this by multiplying myopia by 0.8 and hyperopia by 1.2. As we know, any myopic correction will affect K readings, and this affection will be a reduction in K readings by 0.8 per -1 diopter myopic correction. So let's take this example. A patient has -3 diopter sphere, and if we correct these 3 diopters, the K readings will be reduced by -2.4 diopters. In other words, we can say that -3 manifest refraction equals -2.4 diopters at corneal plane, which we call corneal manifest refraction, and vice versa. -2.4 corneal manifest refraction equals -3 of manifest refraction. The same can be said in hyperopic correction. In hyperopic correction, the K readings will be increased by 1.2 per +1 diopters of hyperopic correction. And if we take this example, +3 diopter sphere will lead to an increase in K readings of +3.6 diopters. In other words, we can say that +3 manifest refraction equals +3.6 corneal manifest refraction, and vice versa. +3.6 corneal manifest refraction equals +3 manifest refraction. Path 2. Outward translation. In this path, we are going to translate the power of the cornea based on K readings into something called assumed manifest refraction. And we do this by multiplying myopia by 1.2 diopters and hyperopia by 0.8. As we know, the normal average K of the normal cornea is 43.5 diopters, and we call this corneal refraction. When the cornea is 43.5 diopters, it is supposed to be plano. And when the average K is higher than this number, so the patient is supposed to have a steep cornea, otherwise he is supposed to have a flat cornea. Now the steep cornea means the patient should have myopia, and the flat cornea means that the patient should have hyperopia. We will take this example. A patient has an average K 46.5 diopters, so this average K is away from the normal average K by -3 diopters. Now, this is called the corneal refraction. We want to translate this corneal refraction into assumed manifest refraction. We multiply this by 1.2, so the patient is supposed to have 3.6 diopters of spherical equivalent. Another example, a patient has 41.5 diopters of average K. So this average K is away from the normal average K by plus 2 diopters. So this patient is supposed to have plus 1.6 diopters of spherical equivalent. Clinical examples. Now we are going to study the TCRP map in two ways. The first one is studying the mean K in order to see the spherical equivalent. And we can study both K1 and K2 when we have sphere and astigmatism. But in both cases, we have to use the 3 mm zone centered with the pupil center. And I'm going to follow this method. We have to use path 1, calculate corneal manifest refraction from glasses or from manifest refraction. We see the corneal refraction at 3 mm on TCRP map. Then we compare both corneal manifest refraction with corneal refraction, and we look for any disparity. The disparity is defined by a difference in sphere by more than 1 diopter, or a difference in astigmatism by more than 1 diopter in amount, or more than 15 degrees in axis. Example number 1. A patient has plus 3 manifest refraction. His corneal manifest refraction will be plus 3.6 diopters. Now we come to corneal refraction. Since we have only sphere, we are going to study the mean K in order to study the spherical equivalent. Now this patient has 41 diopters of average K. So he is supposed to have plus 2.5 diopters of corneal refraction. And if we compare this with the corneal manifest refraction, we find that the corneal manifest refraction is higher than corneal refraction by more than 1 diopter. And this may happen because of any lenticular component or axial component. Example number 2. A patient has minus 4 diopter sphere, and his corneal manifest refraction then should be minus 3.2 diopters. Since we have only sphere, we are going to study the mean K in order to represent the spherical equivalent at corneal plane, and this is called corneal refraction. So his corneal refraction is 0.1. So there is a very big difference between the corneal manifest refraction and the corneal refraction, which may occur because of accommodative spasm, lenticular component, or axial component. Example number 3. A patient has plus 2 diopter sphere plus 1 diopter cylinder at axis 50. This equals corneal manifest refraction of plus 2.4 diopters plus 1.2 diopters at 50. Now, since we have both sphere and cylinder, in this case, we have to study both K1 and K2. We study this by relating K1 and K2 to a scale in which the average K is the plano. Now this patient has K1 is 40.7 diopters, K2 is 41 diopters. The difference between the 41 and the average K is plus 2.5 diopters, and the difference between K1 and K2 is plus 0.3 diopters. Now let us imagine that we are going to treat this patient by plus 2.5 diopter sphere. By this, we are going to push both meridians towards plano. Then we are going to treat his astigmatism by plus 0.3 diopter cylinder in order to make the cornea as plano. So the patient will have plus 2.5 diopter sphere plus 0.3 diopters at the steep axis. Why the steep axis? Because the cylinder is in plus. So corneal refraction of this patient is plus 2.5 plus 0.3 at 50. Now we compare this corneal refraction with his corneal manifest refraction, and as we see, there is no much difference. Example number 4. A patient has plus 1 diopter sphere minus 3 diopter cylinder at 180, which equals minus 2 plus 3 at 90. And this can be translated into corneal manifest refraction minus 1.6 diopters plus 3.6 diopters at 90. Now, since we have sphere and cylinder, so we need to study both K1 and K2, and we relate K1 and K2 to the scale in which the normal average K is the plano. The difference between the average K and K2 is minus 2.1, while the difference between the average K and K1 is plus 0.5 diopters. Now, let us imagine that we are going to treat this patient by minus 2.1 diopter sphere. It means that we are going to push both meridians as follows. And then we are going to treat the plus 2.6 diopter cylinder in order to make all the cornea as plano. So the patient has corneal refraction of minus 2.1 diopter sphere plus 2.6 diopters at the steep axis because the cylinder is in plus. And then we will compare between corneal refraction and corneal manifest refraction, and as you see, there is no much difference. Example number 5. A patient has plus 2 cylinder at axis 100, which equals corneal manifest refraction of plus 2.4 diopters at 100 axis. Since we have astigmatism, then we need to study both K1 and K2 and relate them to this scale, where the difference between the average K and the steep K is minus 1.3 diopters, and the difference between the average K and the flat K is plus 0.1 diopters. I'm going to treat this patient by minus 1.3 diopters. Therefore, I'm going to push both meridians, and then I'm going to treat him for plus 1.4 diopter of cylinder. So the patient has corneal refraction of minus 1.3 plus 1.4 at the steep axis because the cylinder is in plus. Now we compare corneal refraction with corneal manifest refraction, and we see that there is a disparity in sphere and disparity in astigmatism in both amount and axis. So we have to check, especially the topography, and when we check the topography and apply the 12 points, we easily will find that the patient has firm frost keratoconus. So in summary, we use path 1, we calculate corneal manifest refraction from manifest refraction, we calculate corneal refraction from the TCRP, compare the corneal manifest refraction with corneal refraction, and look for any disparity. The second indication of the TCRP map is to determine the assumed manifest refraction in keratoconus and irregular corneas. Actually, there are different methods to determine the refraction in keratoconus. The simplest method is the direct subjective refraction, and this can be used accurately in early cases and mild cases of keratoconus. Contact lens fitting is used when we have moderate and severe cases. The aberrometry can be used when we have mild and moderate cases, but not in severe cases. The TCRP can be used in any case, in any grade of keratoconus, because it reflects the power of the cornea. Now, how to use the TCRP in determination of refraction in keratoconus? We use zone rather than ring, pupil center rather than the apex, and we have to study both K1 and K2, but we need to use the 5 mm zone rather than the 3 mm zone because it is more accurate in keratoconus. We use the same method and the same scale. We relate the two K readings to the scale. Like in this example number 1, the patient has 45.2 diopters as flat K, 48.3 diopters as steep K. Now the difference between the average K and the flat K is minus 1.7 diopters, and the difference between K1 and K2 is minus 3.1 diopters. Now I will imagine that I'm going to treat the patient by minus 1.7 sphere, so I'm going to push both meridians, and then I'm going to treat his astigmatism. So the patient has minus 1.7 sphere minus 3.1 diopters at 20. Now I used the flat axis because the astigmatism is in minus. In other words, the patient has minus 4.8 sphere plus 3.1 cylinder at axis 110. Now I'm going to translate this corneal refraction into assumed manifest refraction by multiplying the sphere by 1.2 and the cylinder by 0.8. So the patient has assumed manifest refraction minus 5.76 plus 2.48 at 110. Example number 2, this is a pellucid marginal degeneration case. The patient has K1 37.9, K2 43.4. Now the difference between the K2 and the average K is plus 0.1, and the difference between the K1 and K2 is plus 5.5 diopters. I will imagine that I'm going to treat this patient by plus 0.1 and then by plus 5.5 for astigmatism. Therefore, the patient has corneal refraction of plus 0.1 sphere plus 5.5 cylinder at the steep axis because the cylinder is in plus. Now I'm going to translate this corneal refraction into assumed manifest refraction by multiplying the corneal refraction by 0.8. So the patient has plus 4.4 at 162. The last indication for the TCRP map is calculation of toric, aphakic, IOL, and we use this map instead of the sagittal map and the SIM-Ks in order to get better and more accurate results. Thank you very much.